So the first example we're going to look at tonight is in my Java 8 folder in my GitHub repository. I will, of course, put up the link to this when I put out the video. But if you go to my GitHub repository and look in Java 8, you'll find this in the EX8 folder. So let's go ahead and take a look at what is in EX8. And there's basically gobs and gobs of examples that show how to use all kinds of features from the Java Completable Futures framework to create, reduce, and or multiply and display big fractions. And this will show us a bunch of factory methods, a bunch of completion stage methods, a bunch of arbitrarity methods, and exception handling methods. Not to mention also, or not to forget to mention, it'll show a few of the basic methods as well, like join. So let's go ahead and take a look at this. There's lots of fun examples here that kind of show you pretty much most of the interesting parts of the Completable Futures API, especially the ones you'll need for assignment 4. So we start out with a field called max fractions. We're going to have 10 fractions when we need a number of fractions in a stream. We have a couple of strings that are going to be basically big fractions, either fractions that have numerators and denominators baked into them, or numerators and denominators independently. And then down here, we go ahead and make a field called S unreduced fraction, which has a big integer, which has this numerator, and a big integer that has this denominator. And we started out to be unreduced. So the flag, the third parameter to value of is false, which means don't reduce it when it's created. And we'll talk more about that a little bit later, because we're going to reduce it in a thread. And then we have ourselves a completed future to void, which, as you can see, is just going to be given a completed future that has the value null. And we'll see how we need that in a couple of places to clean up the code. And then we also have a big reduced fraction constant. So we have an unreduced fraction and a reduced fraction. You can see they have the same value, just one is reduced and one is not reduced. And then we also have a big reduced fraction future, which takes our big reduced fraction and makes a completed future of that value. And you'll see where that gets used later as well. Okay, so then we go in, and you can see we've got about a dozen different test methods we're going to use here. And we're going to use our Async tester framework, which is a really super cool little framework for testing completable futures. We'll see how that works in a second. And we're going to go ahead and register the various test methods with the Async tester class. So let's go take a quick look at the register method. Let's take a look at the class, actually. So Async tester is a helper class that asynchronously runs tests that use the Java Completable Futures framework. And we use this to ensure that the test driver, which is in this case the main program, doesn't exit until all the asynchronous processing is completed. And that's important for asynchronous computations because they're intended to run in the background. And we don't want the main program to exit while this stuff is still going on in the background. We're going to implement this class by having a list of suppliers to completable futures to void. You'll see why we do that in a second. We have a register method that takes a supplier to a completable future to void and adds it to our list. We have another method which we could add, I don't have it here, called unregister if we wanted to get rid of that. We don't need that, so we don't have it, but we could easily add that to remove it. And then down here, we have the run tests method. And what this does is it takes that list of registered suppliers to completable futures to void, and it converts it into a stream. It calls the map method to run each of the registered method references. So it calls supplier.get, which will go ahead and run each of those test functions, those test methods. And then that will return, as you can see, a stream to completable futures to voids. And then we go ahead and use something we call the futures collector. We'll take a look at that, which is going to collect all the results and return a completable future to a list of void. And then when we're all done, we're going to print out how many items were in that list after everything is finished running. And we'll take a look at this collector a little bit later. It's super cool. And you'll get a chance to play around with stuff like that in the upcoming programming assignment. So this is the little helper program that we use here. You can see that we register all these methods. And then in the main thread of control, whoever's calling async tester.run tests, That will then start all the tasks running asynchronously in the background. And then we're going to have the main thread block by calling join until all the background tasks are done. So that's just basically there so that we don't fall off main and cause everything to shut down. That would be completely missing the point of using the async task framework and the, sorry, not the async task, the async tester framework. We want to make sure that the main thread will not return until all the asynchronous tasks that are running in the completable futures framework have all completed. Okay, so let's take a look at these different test methods, and they all demonstrate different stuff. So the first one we're going to do is super simple. It's going to use a completable future and a chain of completion stage methods that are non-async. So you'll see what that means in a second. That means they're going to run in the thread that completed the previous stage. We create a string builder to keep track of the results we want to display. We make a supplier called reduce fraction. You can see what it does is it takes the unreduced fraction and reduces it and prints out some diagnostics and then returns the reduced fraction. So that's a supplier. And we create ourselves a function that takes a big fraction and returns it as a mixed string. You can see what it does. It takes the big fraction and then converts it to a mixed string. We create yet another local variable called consumer, which is of type consumer string. We call print result, and that just prints the result by essentially taking the string builder and turning it into a string and then displaying it. And all display does is just say what the string is and what thread it occurred in. So to kick things off, we say completable future supply async. We give it the reduce fraction supplier. You can see that here. That's going to go off and start that computation running in a background thread from the pool of worker threads. When that finishes, we're then going to call the first completion stage method, then apply, and we're going to pass in the convert to mixed string function, which will convert that to a mixed string. And then the final thing we're going to do is we're going to use the then accept completion stage method to go ahead and take in the print result consumer, which will print the result to the output. And I suppose I should, while we're sitting here, I'll go ahead and run this code. It takes a little while to run, not too long to run. And you can see when it's done, it'll have the results. So here's the results of what we just did. We have our unreduced fraction. It reduced to this improper fraction. We converted that to a mixed string and we printed it out, and everything took place in background thread 30, or 20 rather, 20. So that's where the supplier arranged to run the initial, that's where supply async arranged to run the initial supplier. Okay, so that's the first example. Very simple, just illustrating how you can start some computation running in the background and then go ahead and do these various operations. And when we're done, we are going to be finished. And you can see that we return the result of then accept, which comes back as a completable future to void. So that's what comes back as the return of this thing. So now let's take a look at another example. And this example is going to test big fraction reduction using a completable future and a chain of completion stage async methods. So this is going to be a little bit more interesting. Once again, we use a string builder because it's all going to run in one thread. And actually, I tell you what, I think I probably should be using string buffer here, because these could be running in different threads. So let's go ahead and change string builder to string buffer. Give us better thread safety. The main difference between string buffer and string builder is string builder expects to run in a single thread, whereas string buffer could be called from multiple threads and it would be thread safe. That's the main difference. And you'll see why we probably need to make it a string buffer here. Once again, we have reduced fraction, which will go ahead and reduce the fraction. And we print the results and return the reduced fraction. Once again, we have convert to mixed string, just like we did before. Once again, we have print result, which works just like we did before. But the difference here is instead of using supply async, then apply, and then accept, instead what we're going to do is we're going to use supply async to reduce the big fraction. That'll run in one thread in the common fork join pool. And then we're going to use then apply async. When that result is done, we're going to go ahead and convert to mixed string, which will probably run in a different thread, in a different worker thread in the common fork join pool. And then we're going to call then accept async, which is probably going to do something even different in a different thread. And I noticed I didn't actually put the thread ID where the things were happening, but if I were to do that, they would probably all be running in different threads, because the async methods arrange to run the action that's passed as a parameter in different threads of control. All right, let's now go take a look at yet another test, which is test fraction constant thread. And in this particular case, we're going to use some of the basic features of CompletableFuture and an explicit Java thread. So let's take a look and see how this is going to work. We're going to make ourselves a CompletableFuture that has no behavior associated with it at all. It's just an empty CompletableFuture, as we like to say. And then we're going to go ahead and create a new thread explicitly. So we say new thread, start, and we pass in a lambda expression, or a lambda runnable, or runnable lambda, if you will. And the runnable lambda is going to go ahead and take the result of the big reduced fraction future, which we have created earlier, and we're going to join with it. That will not block because we've already created it. It's already done, just there syntactically. And we will then complete the CompletableFuture. So that basically says, here is its result. And this will then run in the background, and the main thread will then go on and do a little bit more work. It's going to go ahead and call this s.append, but then it's going to call future.join to mixed string. Now, as someone asked on the Piazza group the other day, if you do something in the background and then immediately do nothing but block waiting for the result, was it worth doing in the background? And the answer is no. So you would normally not do this. This is just to demonstrate how you can complete a future and then wait for the completion. So this is not good coding style. It's just demonstrating how you can do the point. In real life, if you actually wanted to do something like this, you would then do something like, do something interesting here, ... And if you did something interesting there, besides just join with the future, then this would be more relevant. This example, again, is just to illustrate how to do completable futures, or to complete a completable future. But you would not want to start a background task running either a normal future or completable future and then immediately join with it. That would be just like making a synchronous call. So no point in doing that. Let's now take a look at a more interesting example. This is going to, once again, use the basic features of CompletableFuture with an explicit Java thread. And what we're going to do here is we're going to make a CompletableFuture for big fraction now, as opposed to what we did up here, which was really simple. And we're then going to go ahead and make the thread, the lambda runnable we give it will create two big fractions and then multiply them together. And when we're done, we're going to complete that CompletableFuture. And once again, I should probably, cut and paste this comment. In a real world program, were you to do something like this, you would do something interesting here. But again, we're just showing that you can do some complicated thing and multiply these things and then complete the CompletableFuture. Having said all of that, it's very rare in practice that you would create an empty CompletableFuture, manually start a thread, and then complete the CompletableFuture in the thread when it's done with its computation. And the reason that you would not do that is because you would more likely use some of the factory methods that come with CompletableFuture to do all this stuff, to avoid having to spawn a thread yourself. So let's take a look at how you might do that. So this is a variant of that. This still creates an empty CompletableFuture. This is called test fraction multiplication run async. And what it's going to do is it's going to use the run async factory method to start this particular runnable running in a thread from the common fork join pool. And then when it's finished, it will give the result of multiplying the two big fractions to complete the future. And then that, of course, will be used to join the result. So we don't have a thread created explicitly, but we're still creating a CompletableFuture that's empty. And that's also somewhat rare. I mean, it's useful to know how to do it, but it's somewhat rare. Let's take a look at yet another example. We're building up closer and closer to the way that you would actually program this stuff, but I'm trying to show you all the different features that are the basic ones at least. So in this particular case, we're going to have a callable that multiplies two big fractions. And so what we're going to do there is we're going to put this in a callable. You probably remember callable is a Java 5 feature. And we have callable big fraction, and it basically takes no parameters and returns a result. In this case, we're going to create two big fractions from the constants and then multiply them together. And then down here, we're going to use the fork join common pool to submit that callable. So we're going to submit the callable. We're going to get back a future to the computation. And then again, just for purposes of full disclosure, you would normally do something interesting here. And then at that point, after you're done doing whatever interesting thing you're doing concurrently, you would then go ahead and get the result of the completable future. Okay, so that's yet another way to do things. Now I think we're finally getting to the point where we're doing things the way that you would really use the completable futures framework. So in the completable futures framework, as I mentioned before, it's very rare that you would ever create an empty completable future and then complete it explicitly. You're much, much, much more likely to do this. You would much more likely say completable future, supply async, give it a supplier lambda, which will be run in a background thread. You get back a completable future to whatever type you have created for the supplier. And oh, by the way, you can also, if you get tired of typing in this kind of stuff, you can also do things like this, which is really convenient once you're using Java 11. You can go ahead and just say var, which is kind of a, I guess it's kind of a JavaScript-like syntactic way. And you can see that IntelliJ tells me that that really is a completable future to a big fraction. So that's arguably a much better way to write it because it's more concise. And then down here, again, with our normal caveat, you would normally do something interesting here. We then join with the result. But now we're getting a lot more like how you'd actually program completable futures in practice. And we'll see more of that as we go further. Okay, now this is yet another crazy way to do things. This example here is just to show a more advanced feature that came with later versions of Java. Again, I would not necessarily recommend doing this type of thing in practice. It's just there to show the feature. So we create ourselves an empty completable future. We tell that completable future that you want to register an action that will append a string when the future is run. So we're going to basically say complete async result equal. And then we're going to use this completely crazy method that was added in later versions of Java. I think this might have come in like Java 9 or Java 11 or something like that. If you recall, we have this thing called complete, which completes synchronously. That's what we've been looking at so far. But now we're going to use the completable future complete async call. And what that's going to do is it's going to complete the future with the result of multiplying two large fractions together. So this is going to run asynchronously, and we're going to multiply these two things together and return that. And then what we call the join method here, it will first call, then run, and then call the complete async call. And yes, I agree that that is completely and totally crazy. And if you come down here and take a look at the results, you can see what you do is it says complete async result equal 2 2/3. So what that's showing is that it's first calling what we register with then run, and then it's calling complete async, and it's taking the results of that and it's returning it and joining those two things together. And yes, that's completely weird. I've never really found a very good description online of why they added complete async. It's just one of those methods that appeared probably for consistency with complete and all the other methods like then apply async, then combine async, then compose async. And they said, oh, we have complete. Let's add complete async. Let's have exceptionally async, right? So they were just being consistent. But this is about the best example I was able to think of to make it do something marginally useful. Okay, so that's kind of the overview of the first part.